Lovely. So thanks a lot, Tamara, for twisting my arm in a nice way into giving the COMET webinar. I'm excited to talk today about the work that I've been doing using satellites to inform seismic hazard and risk in Central Asia. A lot of the work I'm going to talk about today is in our publication, which came out last month. So this is the first shameless plug of this webinar, but not the last. Really pleased to hear. So I'm going to take you to the Tian Shan and let me get my pointer ready. So to orientate yourselves, we have this map. You can see India here, and the area that I'm talking about here is Central Asia. And this is the Tian Shan mountain range. So the Tian Shan is located 1,500 kilometers north of the ongoing collision of India and Eurasia. But it's accommodating a lot of this motion, a lot of this continental collision, hence the mountain ranges and earthquakes. So it's quite a low strain area, which means that the faults are moving slowly, but the earthquakes that happen here can be really large, so magnitude 7s, magnitude 8s. These are really significant events that happen in the region. So the aim of our work and what we've been doing is thinking about the cities in Central Asia, these large capitals and large cities, and their risk because of these faults that they're surrounded by. Earthquakes happen on faults. And so what we want to do is to better map these faults using satellite imagery to understand where earthquakes might happen and the hazard and risk that this might mean for these major cities. I mentioned that there have been a lot of these large earthquakes, these 7 and 8 events, but the growth of these cities since these events has been enormous. So whereas before they were towns with kind of stone and wooden buildings, now they're major cities, capital cities, some of them, and earthquake events now could be a lot more damaging than previously. So most of today I'm going to talk about Almaty, which is in Kazakhstan. So Almaty, you can see here in this Google Earth image looking south, is located at the base of this mountain range. It was previously a capital city of Kazakhstan, but so it moved, and it has a population of about 2 million. So Almaty, like many of the now major cities and towns in the Tian Shan, started as a small settlement and is based here because of factors such as the protection that the mountain ranges offer and things like springs caused by faults giving fresh water. But of course, all of these things, all of these factors and the reasons Almaty is here are largely because of these faults. And these faults are what have caused these major mountains, and now these towns have grown into major cities located essentially on very close to active faults, which have gradually over time formed these major mountain ranges. And here's a picture in Almaty, and you can see it's really dominated the skyline with these snowy mountains, which is a constant stark reminder that these are formed by earthquakes, that there's a constant earthquake risk here. So in order to really understand the earthquake risk to cities, we need to understand the faults that are nearby. So we can identify large faults from core satellite imagery. So what I'm showing you here is topography across the Tian Shan. And if I put on here, these are the faults from the global earthquake models, global active fault map. And you can get a feeling for using the topography and the location of these really high mountains that are caused by faults and earthquakes. We can identify large faults, but actually, what about the much smaller, more subtle faults that could have a very big impact on a city, not just these large ones? So if we zoom in on Almaty now, I'm showing you here, I've flipped to black and white. So this is a digital elevation model, a map of topography over Almaty city. So Almaty is here. This black is showing the outline of the city districts. And to the south here is the mountain ranges, and you can see this goes into the flat of the Kazakh platform to the north. And Almaty is really located at the edge, and the kind of major fault would go along the base of here. So in order to map more subtle features, what we want to do is create better maps of topography. In order to do this, we use some fascinating, exciting satellite data, including spot imagery. This is 1.5 meter resolution optical imagery. And I've shown here the imagery that we have across Almaty, so you really get a feel for the extent of the city and these towns and villages along the mountain range front. As well as this, we use Pleiades satellite imagery. This is even higher resolution, also means it's more expensive. Both of these are paid for satellite images. Then optical imagery, and we have this along the mountain range front through Almaty city, covering a fair chunk of the city. What's really great about Spot and Pleiades images is that for each of those scenes that I showed you, we actually have the same scene taken at 2 different angles. So this is stereo satellite imagery. So you have 2 or even tri-stereo satellite imagery with an extra one coming straight down. And this is useful because by using satellite images taken at different angles, we can calculate topography, we can calculate heights. So this is much like your eyes, how because you have 2 eyes and different angles, this allows you to calculate depths. But instead of doing this using our eyes and our brain, we use Agisoft Metashape and That's Imagine software to take these satellite images taken at different angles and calculate topography across the satellite scene that we have. So across Almaty city, we have lots of different resolutions and areas from these different satellite images that we have. What does this look like? I keep saying high resolution DMs, but to really show you what I mean by this. So this is the freely available digital elevation model, SITM90, it's 90-meter resolution. Almaty city is here, you have to take my word for it as I've annotated it, and here are the mountains. And at this kind of scale, you absolutely can map out these really large faults, but actually identifying something in the city, it's not good enough. So now I'm going to attempt to show you a GIF. So based on my internet and your internet, hopefully what you're seeing is just flicking through different types of topography over Almaty city. And what you'll see is that we start from a very coarse resolution, so you can just about identify the mountains, they're a bit of a blur, but actually as you cycle through, and particularly as you go through Tandem X and the Spot and the Pleiades DMs that we've made here, you're really capturing and seeing all of this detail of the city. And in order to look at really subtle features, this is the kind of resolution that we need. So I'll let it play through once more, just because I enjoy watching it and really seeing this detail come out across the city. In case my internet or your internet wasn't good enough to see that, to really highlight this. So this is again SITM 90-meter resolution. This isn't your eyes. This is a blur at a kind of 2 kilometer stretch. And if you compare it to the same scene that we've made using Pleiades optical imagery to create this digital elevation model. So what you're seeing here is Almaty has a north-south city grid pattern. So I'm trying to show you the outlines of the road. So there's the north-south, you have the east-west. You're seeing individual bridges like here, apartment blocks, individual buildings, outlines of trees along roads. So as you can see on the left, at this kind of scale, you're not seeing any detail at all, but on the right, using this really high resolution satellite imagery, you can really pick out a lot of details of the city. And this is the kind of resolution that we need if we're picking out very small faults within a city, because unlike these major faults that have been around for millions of years and have created high mountain ranges, these smaller faults might create offsets of less than 2 meters. And in order to really capture that, you need this really high level of detail. Oh, and I should say, I put this to remind myself, these point clouds are available on Open Topography, so you can download the point clouds that we've made across Almaty city and play around with this really great data set. So the aim of this high resolution is to identify faults in the city, and one potential fault has been identified in Almaty by COMET scientists, former COMET scientists. So this is visible in the field. So if you look at this picture of Almaty, and as always, the kind of mountains lurking in the background is a reminder of the seismic hazard. But if you follow behind the queuing traffic to where this person is crossing the road, you can see this increase in topography. And this is about 2 meters. This feature, this increase in topography, this uplift is seen over multiple roads, multiple parallel roads. And the city grid in Almaty runs north-south, such that it's very handy for being able to identify faults that may have stepped from the major faults at the base of the mountain ranges into the basin, which in this case is into Almaty city. So we've seen this in our digital elevation models that we've made across the city. And if you look at this bottom profile that we've taken along this road, we've also in the fields taken GNSS, like GPS, measurements along this road and calculated this offset. So we think there's evidence, at least on a few roads in Almaty, of a fault underneath the city that's stepped from the mountain range into the city. Another example is looking to the north of Almaty. So what you're seeing here is colour indicating topography, indicating height. The city districts are shown in light grey, so this is to the northwest of Almaty city, and this red bulge is an increase in topography, and you can see it continues along here. So if we look at the profiles that we've taken over this bulge and look at the elevation, you have this sharp increase and then a shallow tail off, which is indicative of folding, and potentially this could be caused by a fault at the base, creating this increase in topography. Both of these they're really close to Almaty. A lot of the city will be underneath, above these faults, and so understanding the location of these is really key, and using things like satellite imagery to really tie it down is really useful and important. So we've used our satellite imagery to map out some locations of active faults, but what would be really useful to know is that actually what would be the consequences of an earthquake on Almaty city. And for this, we use the global earthquake model's OpenQuake engine. It's a hazard and risk calculation software, and we use scenario mode, which means that for a specific earthquake, we calculate the consequences to Almaty. I'll walk you through the process of this, but it starts by defining an earthquake scenario. And this is very specific, so you pick the geometry, so where is the fault at the surface, what angle does it go into the ground, what's its dip, to what depth does it go, how big is this earthquake, what's the sense of motion, so defining a very specific earthquake. Having done this, the next step is to calculate a map of ground shaking, so how much peak ground acceleration will be caused by an earthquake of this size in this location. And then the really useful things from this is to calculate across Almaty the damage in terms of the number of buildings that are damaged and collapsed, and the loss in terms of economic replacement cost and fatalities. So there's a few things that a few inputs that we need for this flowchart, and I'll go through each one in turn. So starting with defining the earthquake scenarios, we've identified a couple using our satellite techniques. But I mentioned, or maybe I didn't mention, that there have been several large earthquakes that affected Almaty in the past. So this is an interesting place to start, to see that now that Almaty is a much larger city, what kind of effect would this have if they were to happen today? So the first historical scenario that we model is the Verny earthquake in 1887. So Almaty was originally known as Verny. It was a small town at the time. Thanks to Russian geologists coming out after the earthquake and doing a detailed report, we have a lot of details about this earthquake. Haven't found the surface rupture of this fault, so where the fault breaks the surface. So don't know for sure where this earthquake might have been, but using isoseismals from mapping at the time, we have an estimate of where it might have been. So for an input into the OpenQuake engine, in order to calculate our hazard and loss, we use a fault geometry like this. So red is the faulted surface and blue is the faulted depth. You'll notice it's a big rectangle. Don't tell the geologists, of course, faults really aren't this simple. A fault zone is an incredibly complicated thing, but here we've mapped it very simply, so apologies to geologists in the audience. So this is the first of our historical scenarios that we modeled to see what would be the effects if it were to happen today. Just 2 years after the Verny earthquake, there was the Chillik event. This was much larger, whereas the Verny was about magnitude 7.3. Estimates on this range from magnitude 8 to 8.3. So this is big. This is a really large event. It's been well mapped by collaborators and co-authors and COMET scientists as a really interesting structure. So instead of kind of being a simple fault plane, it's a host of interacting faults. Some thrust, so reverse faults, some strike slip, so a range of different motions. So really interesting type of event here. So again, this is showing Almaty in the city district, and here's how we've modelled it largely as vertical faults because they're strike slip. We've modelled it as a magnitude 8. The final of the historical events that we model here was in 1911. So yeah, really close to the other events. Almaty was affected by a lot of earthquakes very quickly, and this again is a really big, significant event. So magnitude 7.9, magnitude 8. This is really huge, and I think this for me is one of the times where I really got to appreciate a big earthquake without ever having been in one myself. Because in this top image, what you can see in red is the fault mapping from Smith et al. So this is where the fault has broken the surface during the earthquake. And what you'll see is that this rupture goes along for hundreds of kilometers. So we drove along this valley and we saw these fault ruptures, and it just continues. We drove along this valley for hours, and you just continue to see the effects of this really large earthquake. So for me, this is one of the times where I really appreciated the scale of the kind of events that we're looking at here. So this is a large event. Based on this fault mapping, we model it as 2 faults dipping to the north. So one plane here and one plane here. So here are the 3 historical earthquakes that we model. Then based on fault mapping and our knowledge of geology in the area, we define a number of hypothetical scenarios. So on the left, this city splay, the photo that I showed you of that uplift in the city is around about here, and the kind of evidence is on a few parallel roads here that we've continued across Almaty to join up with the main mountain range fault. This fold, potentially have a fault underneath it to the north, we've put here, and as you can see, it extends under a lot of Almaty city. And then COMET scientists mapping to the east of Almaty, we've used this fault over in the Talgar area as another hypothetical scenario. We've also looked at the effects of, instead of to the south of Almaty, looking to the north. So you'll see here that it changes from this kind of mountainous very suddenly to the flat, strong Kazakh platform. So we've put a large hypothetical event here to kind of understand the effects of this, as it's a different kind of geology, as we have different effect to Almaty. So we've got those 3 historical events and these 4 hypothetical events to put into OpenQuake engine. And so the next step is to calculate, due to each of these specific earthquakes, their geometry, their size, is to work out what kind of shaking would happen across Almaty due to these. In order to do this, we use ground motion prediction equations. So as it says on the tin, these are equations that predict the amount of ground motion based on the distance from an earthquake. So here I'm showing you for the 3 different GMPs, ground motion prediction equations that we use, a graph of peak ground acceleration as a function of distance. So as you expect, the general form of this graph is showing very close to an earthquake, you're expecting high acceleration, and this gradually decreases as with increasing distance from the earthquake. There are a whole host of different ground motion prediction equations. I'm sure many lectures on just this topic, but we've chosen these 3. They're for shallow tectonic regions. I guess we've used a different one for our earthquake to the north in the Kazakh platform. And we calculate the average of these 3 for figures going forward that I show you. We'll notice as well there's small differences between them. There's a lot of assumptions that go into these, and you can go back to the original papers and really tease out all these different assumptions. And there's also these different values here, 300, 500, 800. And so in order to have an estimate on the amount of ground shaking, of course, we need to understand something about the ground. And so if you were to shake sort of soft sediments compared to a strong rock, then you're going to get a different amount of shaking, the same amount of seismic AG input. And so an input for this is VS30. This is called it's the shear wave estimate in the top 30 meters. We use estimates calculated from topography, USGS estimates, and this gives an indication of how the terrain might react and use this to work out the amount of shaking. So you can see Almaty districts in black, and to the south where the mountain ranges, we get very high values compared to lower in the north. And this is a way of allowing for differences in the geology and the rocks to work out the different shaking that might occur. So we have our earthquake scenarios, we have our equations and a host of inputs, and from this we can calculate, here I'm showing peak ground acceleration across Almaty city. So I'll show you a number of figures that look like this. So on the top we have our three historical events, so the Verny, Chilik and Chongqing events, and on the bottom we have our hypothetical scenarios, and you're seeing peak ground acceleration across Almaty city in black. One thing you'll notice for events where the fault extends into the city, again, I've got the fault with red at the surface and blue at depth. And you'll see that particularly for these equations, if for terrain that's directly above a fault, the shaking is significantly increased. So particularly for the city spray and northern spray, seeing really high acceleration across Almaty because it's located directly above these faults. Also because these are smaller, we've modelled them as magnitude 6 compared to these larger events, but a lot of the patterns that we're seeing are because of how much of the city is directly above these faults. So for example, comparing the magnitude 6, and this is a similar magnitude 6 but to the east, but actually because of this decay that we saw as distance from the fault, the shaking across Almaty is significantly less for the same size event. So we have the shaking across the city, but what we really want to know, what would be really useful, is damages and losses. So in order to do this, in order to work out how many buildings would collapse, we need to know something about the buildings. So in order to do this, we use something called an exposure model. So the one for Almaty and actually Bishkek and a number of cities across the Tian Shan is created by the GFZ group over many, many years. A huge chunk of work involving field survey, screening, local engineers, driving a car with an omnidirectional camera up and down roads and cities, and high resolution satellite images. So this is the model that we use for Almaty. So you can see here we have estimates of the number of buildings across the different districts in Almaty, and also these the information about buildings needs to be very, very specific. So not simply the number of buildings, but also precisely what they're made of, including, you know, their overall material and walls and ceilings, and how tall they are, how many stories, because of course the height of the building will make a really big difference to the amount of shaking that it experiences. So as you'll see here, this is the different building materials used across Almaty in this exposure model. So there are relatively few wooden and steel buildings, there are a handful of concrete, but mostly it's masonry and brick buildings. And a high percentage of these are unreinforced, so just bricks, not reinforced with metal bars or confined to add strength. So this is a very common building type. And I should say right here that we're looking at residential buildings. So there's also information for industrial and commercial buildings, but here we're looking at residential buildings. So the totals that I'm showing you and the results that I'm about to go on to show you are all for residential buildings. So now to show you the results of our calculations, and again you're seeing it will be the three historical events on the top and the four hypothetical on the bottom. What we've done is for each district in Almaty to kind of get a feel of the spatial distribution across the city is to sum the number of completely damaged residential buildings for each district, and the totals are here, and these percentages are showing the percentage of buildings in that district that are that show complete damage. There are also buildings that have severe, moderate and slight damage, but here we're just showing the completely damaged buildings. So this is for the Verni earthquake, compared to a town of, I think it was 25,000 buildings, 25,000 population. I can't remember the exact numbers, but there are a lot more buildings now, and our total is much larger. In contrast, the Chillik event, this is a much bigger earthquake, magnitude 8 compared to 7.3, but because of its distance, the ground shaking that we saw on it previously is much lower, and so the values that we're seeing are much lower across the city, but this is still a significant event. This is still thousands of buildings damaged. And likewise for the Chongqing, you don't see the spatial distribution as strongly for Verni because this district is directly above the fault, so a more even distribution across the city, but this is a significant event. So now I'll go through the hypothetical scenarios. This is for the city splay, and if I show the northern splay as well, you're really seeing, again, like with the Verni example, that the districts directly above the fault experience really high values. So you get quite a varied distribution across the city and really high values because the shaking is so great directly above the fault. These are really significant events. I've flashed these up as well. Even though, as I said before, this is the same magnitude, because of its distance and not being located directly under Almaty, the shaking is much less for Talgar, and this is reflected in the damage. And the same for the Kazakh platform. So to show you them all, what your eye is immediately drawn to this northern splay event, and it would be very significant. As all of these would, in contrast to these closest events, the more distal events are still causing thousands of buildings collapse. So significant for Almaty. Likewise, we can calculate the replacement costs, so the cost of replacing the residential buildings, and you see a very similar distribution across the city districts. Of course, there are some differences because not all districts have the same value residential buildings, but essentially you're seeing a very similar effect where districts directly above faults, because of this increased shaking, because of the increased building collapse, have a higher cost to replace buildings in that district. And finally, the fatalities. So these are all significant events. These are all hundreds of thousands of fatalities, and would be terrible for Almaty. You'll notice that these percentages are much lower, so than for the total number of buildings collapsed. So I think for Verni, you're seeing maybe around 20–30% in this district for building collapse, but the fatalities are much lower. So even in buildings that collapse, only a small, relatively small number of fatalities would occur. So these are much slower, but still Almaty is now a population of nearly 2 million people. And so all of these events would cause significant fatalities. Going back to this flow chart, so we've kind of defined our earthquake scenarios and done the run through and calculated for our specific earthquake scenarios the damage and losses. Now think about areas here that we might be able to add improvements. So one is thinking about the details of the fault. So to give you an example, we're geologists very interested in faults, and whilst I'm showing these offensive rectangular faults, actually the geometry and location of where these active faults are is of great interest to us. And so here in orange is this the fault ruptures from the Chongqing event, and based on Aris Mefasal's work. And there are different ways that we might look at this mapping and think about where a fault is. So before, I've shown you a kind of two fault scenarios, so one here and one here, kind of matching this mapping. But equally, perhaps this is one large fault and it goes somewhere like here. Or maybe using the details from this fault mapping, looking at the surface and understanding which ways the faults are dipping, the angle, which way they're going into the ground and the angles, we could create a very complex fault model. And sometimes it can be very hard to say which one is right, but does this make a difference? And what we see is that it does make a difference. So Again, these are the Almaty city districts. This is a different scale to the figures that I've shown you before. And this is for the one fault, the two faults, and a complex fault model. So these are similar events. We've only changed the geometry of the fault, so it's the same magnitude. They're all thrust faults. But what you'll see is that the two fault setup shows consistently higher values across all of the city districts compared to the one fault and the complex fault models. And the reason for this is because if I take this yellow box away, just in blue, you can see the extent of the fault. And because of the geometry of this fault, it's much closer to Almaty than the others. Oops, wrong way. And so because of this, because it's that much closer, it's causing that much more damage. So 6,500 compared to 4,500. So understanding the geometry to the faults can actually have a really big impact on our estimates. And another example of this is not just the faults at the surface, but also the faults at depth. So here I'm showing you this northern fault, Almaty districts in black, and the fault here, the surface in red, dipping under Almaty. And this is the damage that I showed you in the compilation video before. But for this fault, what we assumed is that if this is the surface, we assumed that the fault started at the surface and dipped at 45 degrees to 20 kilometers depth. But actually, we don't know that the fault does this. And looking at the folding, it could be possible that the fault, instead of dipping at 45 or kind of angle from the surface to depth, it could dip and then shallow at quite a shallow level. So we take a look and see what difference this would make. And as you can see, for the peak ground acceleration, for the ground shaking, the difference is really large. So because this part of the fault is now significantly closer to the surface, to Almaty city, than it is in the simple 45-bit model, you'll see that the shaking is now much larger across a lot of the city. And actually, this makes a really big difference to our estimates. And so it's 40% more damaged buildings and a really high 38% more fatalities, 27% higher replacement cost. So understanding for these faults close to the city, their geometry, it can make a really big difference to our estimates. So this is something that geologists we can help with by understanding the faults and their location and what they do at depth. And also, I think there's more work to be done in the ground motion prediction equations. So these equations that calculate the shaking can give different values. They're all based on different assumptions, but what's the best one for understanding what kind of shaking would happen at the surface for a fault that looks like this? So there are different ways that fault geometry improvements can improve models like this. Another area in this flowchart that we can add improvement is towards the end. I mentioned that it's vitally important that we have the details of the buildings in order to calculate the buildings that collapse and the losses that might occur. And in order to collect these building details, I said the GeoSed group, it's years and years of extensive work across Almaty and Bishkek and many cities in the Tian Shan. They've used satellite imagery as well, so high resolution imagery to group different building types together and to identify building outlines and things. And this is a really good example of how satellite imagery can be used to cover a whole city and be updated. So if you can identify buildings that are similar to each other from satellite imagery, then instead of the need for yearly field campaigns as a city grows and expands, then maybe satellite imagery is a way to do this. And as I've mentioned to you before, and I showed you in the GIF of heights, we have estimates of building heights across the entire city. So we have topography, and potentially we have estimates for every single building potentially. But is it accurate? Can it be used to better inform an exposure model? So we looked at this, and in the field we used a laser rangefinder to estimate the height of 15 different buildings. So that's this black dot. And then using our different satellite scenes, so we have one spot and two stereo clearly seen and one tri-stereo, and we looked to see how accurately they could cover this building height that we measured in the field. And you can see that generally they are underestimates, but in general they can, and particularly Pleiades tristerio, can retrieve a reasonable building height. One obvious example where this didn't happen is for the spot DM for the particularly high buildings. So remember that spot is lower resolution than the Pleiades, and we found that these tall buildings were just removed as noise, and every different filtering and every program that we tried removed them as noise. So we weren't able to retrieve heights for these high buildings. So this is interesting to note. So if you wanted to roll this out across an entire city, there isn't time to check individual things like this. But spot is much cheaper than Pleiades, so there's a balancing act there. But in general, the highest resolution in Pleiades tristerio performed the best. So this is exciting because we potentially have reasonable estimates of building height across the city. And so Scott Watson, COMET scientist at the University of Leeds, is doing some really exciting work across Bishkek. And so using the satellite imagery that we have, and again, we have Pleiades tristerio in the region, training in an algorithm to automatically identify all of the different buildings, and then extracting the building heights that we have across the city using these polygons and assigning building age using optical imagery, and to then get building type, which could help inform exposure model. So watch this space for exciting things for you, Scott. So I've got a little while left, so I'd like to talk to you about some work that we've just submitted this paper, and we're looking instead of Almaty, we've switched now to Bishkek. So like Almaty, Bishkek is located near the mountain range front. There are a few differences here. So one is that you'll see these really high mountain ranges, but you'll also notice these hills. So this is looking south from Bishkek. So here the faults have already stepped into the basin and are forming these low hills as well as these high mountains. So I'll talk through quickly some highlight results from the work we've been doing in Bishkek in Kyrgyzstan. So I'm looking now, this is a map, so in black these are the Bishkek city districts, and these hills that you saw in the Google Earth image are caused by this Isagata fault. Bishkek is very close to the Chonkochak and Shamsi Tunduk faults. And like Almaty, there is a history of earthquakes that have happened in this region and that are known to have affected Bishkek. We also use satellite imagery to look at if there are any faults near to Bishkek that could potentially be active. So here you're seeing colour indicating topography, and in blue is the Bishkek district. And similar to Almaty, we're seeing this increase in topography to the northeast of Bishkek. And again, if you look at one of these profile lines, if you look at profile B, this increase in elevation is very sharp. Be indicative of a fault here, which again is very close to Bishkek and potentially dip under the city. So in my whistle-stop tour of the work that we've done, here are the 9 potential earthquake scenarios that we've modelled here. So again, Bishkek is in black, Almaty is over here off the page. And we've got in purple some historical events that are known to affect Bishkek, particularly the Belovedosk events, and smaller one here, and in red a host of hyperthermal events based on fault mapping, and some that we've done and some from literature and things. Particularly the Isagata fault, so the Belovedosk earthquake occurred on the Isagata fault and could potentially have loaded the rest of the Isagata fault, and this is the closest fault to Bishkek. And it's big, it caused a big event. So I'm sure you won't be surprised if I tell you that what we find is that the Isagata fault is the most damaging of our 9 scenarios. And this is because of its proximity. It's caused high peak ground accelerations across Bishkek. And if we look at the sum for the 4 Bishkek districts and the percentages indicated by these bars, it's because it's so close, it's causing a lot of damaged buildings. And again, because it's so close, there is some kind of spatial distribution across Bishkek, but actually it's very high across the 4 districts, high percentage damages. And replacement costs and fatalities. Because I haven't got much time, as a different way of showing you the impact of these different scenarios, I've got this kind of infographic here, which is trying to think of different ways to simply show our results. You'll notice the Russian here. And so here we're showing visually, hopefully simply, the number of completely damaged buildings. So these are our 9 different scenarios, and your eye is immediately drawn to this Issachar Revolt as being the biggest, and particularly these 4 high magnitude, in contrast to events that are further away but are still significant. And again, I was going to say as well, so completely damaged buildings, as well as completely damaged buildings, we have buildings showing no damage, slight damage, moderate and extensive. And so for this Issachar event, here is kind of showing the distribution that we see. So this is the number of complete damage that I've been showing, but you can see here visually the number of buildings showing different damage states. You see a similar pattern, but again there are slight differences for replacement cost and again for fatalities. So this is a visual way to very simply and quickly indicate that you're really seeing these are the large events. So what we learned from this, what are our recommendations? And when you delve into the numbers of the buildings that are collapsing, it's the unreinforced masonry buildings. So hence in the name, they're unreinforced. They don't have the poles in them for the reinforced masonry, and they're not confined by concrete, and so they're very vulnerable, fragile to earthquakes. This is at the Bishkek districts, and in Bishkek and in most of the districts in Almaty, they're the major building type for residential buildings, unreinforced masonry buildings. So our recommendations are that the buildings should be retrofit, so they're less likely to collapse in earthquakes. They're made stronger, so they're more resilient. And it should start with unreinforced masonry buildings, and that new buildings shouldn't be made of unreinforced masonry. They should be reinforced and confined. So you might be sat there thinking, why on earth is she telling me these recommendations? I'm not the person that needs to know. And so working with our collaborators in Kyrgyzstan, without whom none of this work could have happened, so many thanks to you if you're listening. We've prepared a recommendations document, and so this summarizes our major findings, what we did, what we found, and our recommendations, particularly with regards to retrofitting and unreinforced masonry buildings. You'll see here we translated it into Russian, because of course, what's the point of having something in English? And so we've been working on this closely with our collaborators, and this whole work has been a close collaboration with the people who live closest to these faults and who understand it. So we hope to pass this to the Ministry of Emergency Situations to show the work that we've done. And just to end, a really exciting and important part of this work has been capacity building. So it's all very well and good for me as a researcher to do this work, but actually my postdoc has come to an end now. So I'm about to disappear into the wind and take this knowledge and skills with me. So what's really important to do is for people who live in Bishkek to be able to do this, so that actually they can, start from the models that we've done here, but in the future, if they want to change them, then to have the knowledge and the software and the skills to use them. And so that's what we've been doing with Sultan and Gulkaya. So this is when we met in the summer in Bishkek during fieldwork in Kyrgyzstan. And then they came over to Leeds in Christmas 2019 for a tough month of learning how to use OpenQuake, different input models, all the things that we've done in order to be able to do the kind of things that I've shown you today for themselves, so that in the future they can update these models and understand them and teach other people. It's been very hard over the pandemic. If they're listening, I'm sure they'll agree that that debugging via Zoom in a second language is difficult. So they've worked very hard, and it's been a joy to work with them. And this has been, a really important and really great part of this project. So I'm just about at 45 minutes. Couldn't have done that if I tried. So just to leave you with my conclusions. Said multiple times, there are lots of cities in Central Asia at risk from earthquakes, and I focus on Almaty and Bishkek. It's kind of larger cities, but there are plenty. There's so many faults, earthquakes, and those places are at risk. We can use high resolution topography maps in order to identify fault zones in the city. And a really useful thing that we could do as scientists, as geologists, is to better understand the faults and understand how they work at depth and how they interact and their location, and then what size earthquakes they could host in order to inform models like this. Our estimates show that for scenarios in Almaty and Bishkek, these events on these very proximal faults could be thousands of collapsed buildings and likewise thousands of fatalities. And so our recommendations really are that to retrofit the buildings and to focus with unreinforced masonry buildings and to target these across the different districts. And here's my other plug for the paper again. This is for the work for Almaty, and tune into my AGU talk to hear more detail about the work we've been doing in Bishkek. So thank you very much.
That was brilliant. Thank you so much, Ruth. I'm very impressed with your timing, but also fantastic talk. I really enjoyed it. There's already 2 questions, so I'm going to save my questions to in lieu of other people. One has come in from Rob Govers, apologies, Rob. So it's great presentation, Ruth. A similar analysis would be very useful for critical infrastructure like bridges and highways. Why was this not included yet?
I think the classic excuse, lack of time. So yes, absolutely. I think it's useful to know, fatalities and damage, but what would be really useful is knowing things like injuries and how they're distributed throughout a city. So yeah, damages to critical infrastructure, how many injured people are there going to be, and are they close to a hospital? So this is, yeah, natural extensions of the work that we didn't really have time for here, but they're estimating injuries. Again, it very much depends upon whether the vulnerability curves are developed, and so they are for Central Asia. There's a lot of work by the Global Earthquake Model to develop these kind of curves that calculate for this amount of shaking, we estimate this many buildings would fall down and this kind of losses would occur. There are for some regions for injuries, but not particularly for here. There are rules of thumb that you can use, and maybe for developing countries like these, that you could expect 10 or 15 times as many injuries as fatalities. But yes, going into details, and this is partly why we took this kind of district approach, is to really understand not just the totals, but also how it's distributed and how that could affect railways, hospitals, bridges, like you say.
Brilliant, thank you. I'm going to move on to another question because we have 2 more already. If you have any questions, do put them in the chat or the Q&A. So from Alex Hatton, Ruth, great work. I'm curious about the variable fault complexity comparisons you shared at the end of the Almaty portion. You point out that the 2 fault model has higher damage proxies as the proximity of the fault is closer to Almaty, but it seems that the fault plane area is greatest in the 2 fault model than the single of complex iterations. It looks like the ramp flat geometry also added fault plane area. So additionally, I'm curious about the magnitude frequency used for these calculations. Can you comment on the influence of fault plane area and magnitude frequency distribution scaling relationships on these comparisons? That was a lot, but you can also read the question if you got confused.
Yeah, I think I've got it. So yes, so the equations that we use, these ground motion predictions equations, they're not, as geologists, we might think about, the earthquake, the slip on an earthquake, it's and the kind of magnitude of slip and things like this. But these equations, they're not looking at it in the same way. So they're empirical equations based on past data from events, and so they're simply not simply, it's very complicated and I couldn't do it myself, but calculating shaking as a function of distance to the fault. And so actually a lot of what I've done, as long as the distance to the fault doesn't change, of course, whatever distance it might be, that's kind of the key factor here. So actually you might be thinking, if it's a larger fault plane, then there's slip could be spread across a higher area, or maybe it's decreased slip of a larger area, or things like this. But actually, none of that is really captured in the ground motion predictions equations. It's just the distance is the key factor in these. These aren't the only ways to model shaking, and it's a frequently used way. And there are a whole host that you can choose in the global earthquake model, but yes, it doesn't go into the kind of earthquake physics as much as you might be hoping. It's distance, and in fact different ground motion prediction equations use distance in a different way. So it could be the ones that we use take into account the distance from the fault to the surface, and that's why we see these different distributions, whether we do a ramp flat geometry or a simple 45-degree different fault. But some just take into account whether it's above the fault or beyond the fault, and then scale. There's others that do from a hypercenter. So a host of different ways, but the key is it's distance, so not the full kind of earthquake physics that you're hoping for. I hope that answered all of your multi-part question.
Cool. I'm gonna, Alex, if you have any follow-up questions, do put them in the chat. I'm gonna ask one of these other questions. So this comes from Liz Vanacore. Given how inaccurate the VS30 from topography can be relative to actual site measurements, are there plans to improve this critical model input by incorporating or retrieving data from active source? Oh, I don't actually know those acronyms. Active source, MASW, or HVSR, etc. Given the geology side effects are likely highly influential on the ground shaking.
Yes, you're right. You're right. I don't know the acronyms either, I'm afraid. So the thing with the estimates that we have, so they're the USGS estimates, so they're based on topography. So making an estimate of the kind of terrain based on how steep the slope is. So the good thing about it is that it's across the entire city. It's coarse and inaccurate, like you say, but less time consuming than taking these measurements. So we don't have plans to take these type of measurements, but like you say, they would improve the calculations. One thing we did think about is that in the same way that we have buildings across the entire city, we have topography across the entire city, and actually, would it be useful for us to derive a higher resolution VS30? But I think we discussed this a lot and decided essentially that actually producing maps of VS30 from slope is in itself coarse, that using a better slope map isn't really going to add much. So that's why we didn't do that.
Well, thank you. And yeah, if you have follow-up questions, do put them in the chat. We have another question, which I'm going to combine these two questions from Monghan Huang, who says, thank you for the amazing analysis. Maybe you already mentioned this in the talk, but what is the tectonic loading rate? In other words, how often do you anticipate a magnitude 6-ish event in the city? And also Zoe Milton has asked a similar question of, do you have constraints on the recurrence intervals of your modeled earthquake scenarios?
Yeah, so we haven't touched upon those here, and I don't have the good answer for you at all. Yeah, like say how often these earthquakes are going to occur is very important. And we've taken the scenario approach based on, from our geology knowledge, this is an earthquake that may happen, and these are the consequences that we would see. So I don't have an answer for you. We know, particularly the historical events, we know that these kind of events have occurred and can occur. But yeah, this is a natural extension to the work to kind of put magnitude frequencies, estimation of recurrence times on them.
Yeah, I guess I'm just going to, there are two more questions, but I just want to butt in. From a policy perspective, do you think that it matters what the recurrence interval is if you're talking to government? Like, are they more interested in looking at these damage estimates or the frequency that they might expect those damage estimates?
I think from an engineering perspective, and quite often understanding the peak ground acceleration periods is a useful thing to know. And I guess also the thing is that obviously I'm sat here as an earthquake scientist thinking about earthquakes, but also I guess you, as a policymaker, you need to put this in context from all the other natural hazards that might be occurring in the city, like global pandemics and flooding and et cetera. And so I think it is a useful thing to kind of put in context and say, compared to your annual risk of whatever it may be, here's another thing.
Cool. Okay. Alex Hatton has posted another follow-up. So she's coming at this from an earthquake rupture forecast point of view, so it makes sense that ground motion equations care only about distance to the fault. I would think, though, that return time of the shaking events would change based on the fault parameters. She says, I'm just a hopeless geology wishing that faults move the needle.
Sorry, so
So she thinks that the return time of the shaking events might change based on fault parameters.
as in, I'm not sure I understand this.
Yeah. Alex, chuck in another comment, Alex, if you want to follow up. Oh, Chris, yeah.
Loading rate and locking depth and stuff like that. And maybe how many different faults were taking up the slack in conjunction with one another. But yeah, I guess if this is more deterministic, it sort of is, well, assuming something goes off, what it is going to do.
Yeah, I see your follow-up. Yes, and so certainly if you were thinking about how these, if one of these events were to occur, then that would mean another one is less likely to occur because of the strain release, etc. Send me an email, Alex, so we can talk about this later.
Yeah, I think that, I just from my own perspective, I dealt a little bit with strong ground motion equations, and geologists, I think, I don't tend to get along very well with strong ground motion equations because they don't take into account all the things that I think are important as a geologist.
Yeah, and I spent a lot of my PhD thinking about the slip distribution in an earthquake and what kind of relationship this shows and how we can calculate it better. And again, it's not captured. It's not captured.
Yeah. Okay, there's another question from Alberto Pizzi. What do you think could be more useful and that can be further implemented in the analysis of satellite images, mapping interpretation of the DTM, or use of serial profiles? I'm not sure what serial profiles means. Maybe you can let us know, Alberto. But so I think just what is the most useful advance then in analyzing the satellite images?
So I think one thing is kind of identifying these really subtle features. So I think it always needs to be backed up by field work. So I think unless I've put my eyes on it myself, I'm uncomfortable calling it a fault. But I think with this high resolution, we can easily look across our whole city. So we can take profiles across. I see your chat. Topographic profiles across roads and cities and really analyze on a large scale. Are there topographic increases? Are they consistent across roads such that this might be indicative of fault? So I think it's kind of ongoing benefits of satellite data is it's large scale. You can get it across an entire city and analyze it like this. And I think that the potential to improve the exposure model is really exciting because all of the things that I've shown you here today are resting upon our values of what the buildings are and where they are and what they're made from and how tall they are. And of course, the second that you write down these values, there's a new building development and they're out of date. And so you need to do it all again. And so I think, watch out for publications from Scott kind of looking at how we can automatically detect, work out the height, work out what the building type might be based on its similarity to other building types. So I think that's a really exciting review. And I'd be interested to see, what kind of difference it makes to the calculations that we can do and what kind of, it's really important for as cities grow, particularly developing countries where maybe we don't have, as much resources to go out and really map out these things in detail. But I think that's a really exciting aspect.
Brilliant. Thank you, Ruth. I know we're on 5:03, but for those who are still with us, I actually have a question that I wanted to ask.
Okay, go for it.
I wondered if you could comment on how easy or useful it is for a geologist like me to map out a fault, map out the geometry of the fault as best I can, and then to use this sort of technology, do a similar sort of analysis to understand what the risk might actually be to people around that fault.
How easy it is to kind of
how easy it is to use the process and methodology that you've put in place. Is it something that all of us can do, or is there a lot of nuance so you have to kind of specialize in order to understand what you're actually doing?
Yeah, I think so on the one hand, so the global earthquake model, the OpenQuake engine, it's all open source, so you can go and see all of it, you can add to it. So if there's a ground motion prediction equation you want that isn't in there, you can add it in. So on the one hand, it's all readily available, but I'm going to say that all of the work that I've done here has been in really close collaboration with Marco Gani and Vitor Silva at the Global Earthquake Model. And like you say, there's a lot of nuance, and I think you could quite easily take your fault and input and get an output, but actually making sure that you understood, you know, which ground motion prediction equation to use, whether you use this correlation. These are, as also as we know, that there's uncertainties associated with these ground motion prediction equations. So whether you run them for 100 iterations or 1,000 iterations, and there's a host of things. So so I thoroughly recommend collaborating with any scientist at the Global Earthquake Model to really understand the ins and outs. So you definitely can, but I think to make sure that you fully understand, yeah. And I've written a bunch of help documents to try to extract the knowledge from my head and put it on paper. So if anyone's interested, I can send it round. And again, it really depends on your exposure model. So if you're interested in, you know, in Central Asia, there's this huge bank of work working on it, but actually if there were a different area, your outputs are only going to be as good as those. So even with our increased knowledge of the faults, if what you want is the risk, if you want the damages and losses, then it's really based upon, you know, does it exist already, and how high resolution it is, and when it was last updated.
Yeah, that makes a lot of sense. Okay, well, I think that's all the questions that we have in here, and we are 5 minutes over time. So I think that is probably a natural end to the talk. Thank you so much, Ruth. That was wonderful. And all of those questions and answers were very, very insightful. And thank you for coming along to present to us today.
Great, thanks very much.